The airlock fails, and you're suddenly exposed to open space with no suit. Movies have trained you to expect an instant, gruesome explosion. Here's what actually happens instead. You have about 10 seconds of useful consciousness left, and your body handles the vacuum in ways stranger, and somehow less violent, than fiction ever shows. That's the real answer to today's question. What if you were exposed to space without a suit? Not the Hollywood version, with bodies bursting apart on contact with vacuum. The actual, documented physiological sequence, part of it confirmed by a real accident inside a NASA test chamber. This isn't purely theoretical. In 1965, NASA engineer Jim LeBlanc was testing a spacesuit inside a vacuum chamber at Johnson Space Center when his suit lost pressure completely, exposing him briefly to a near-vacuum environment before an emergency team could act. He survived, and later described feeling the saliva boiling off his tongue in the instant before he lost consciousness. Colleagues in the chamber's control room rushed to repressurize the space within about 15 seconds, and LeBlanc regained consciousness shortly after, with no lasting harm. That one accident gave researchers real human data on exactly what the first seconds of vacuum exposure feel like. Data that still shapes emergency training for astronauts today. Here's the one concept you need. Your body is built to operate at roughly 1 atmosphere of pressure, the same pressure holding your blood and other fluids in liquid form at your normal body temperature. Water's boiling point depends heavily on surrounding pressure, not just temperature. That's why water boils at a lower temperature on a high mountain than at sea level. Remove that surrounding pressure almost entirely, the way open space does, and water can start turning to vapor at ordinary body temperature instead of the usual 212 degrees Fahrenheit it needs at sea level. This isn't your blood boiling from heat, there's no heat involved at all. It's a pressure effect called ebullism, and it's the single most important thing happening to your body in vacuum. So let's walk through it, stage by stage. First, within the initial second or two, any air still in your lungs would begin rapidly expanding as the surrounding pressure disappears almost completely. If you tried to hold your breath, the way instinct tells you to, that trapped, rapidly expanding air could actually rupture lung tissue from the inside. NASA's own guidance is the exact opposite of instinct. Exhale immediately and completely, and let the air leave your lungs freely rather than fighting to hold onto it. Then, within about 10 seconds, your blood begins losing oxygen at incredible speed, not because you're technically suffocating yet in the traditional sense, but because the near-total absence of external pressure pulls dissolved gases out of your bloodstream, straight into your lungs and surrounding tissues, the reverse of how a soda goes flat the moment you crack open the can. This is what actually causes unconsciousness so quickly, faster than simple lack of oxygen would explain on its own, and it's the reason NASA describes roughly 9 to 11 seconds of useful, functional consciousness before you black out. Meanwhile, moisture on exposed surfaces, your eyes, your tongue, the surface of your skin, genuinely does begin to vaporize, exactly as LeBlanc described decades ago. Your skin itself is elastic enough to contain the pressure building underneath it, so you would swell noticeably, potentially up to roughly twice your normal size, but your skin would not rupture or explode the way movies so often depict. Human skin turns out to be strong enough to hold that internal pressure differential on its own. Here's the twist most people get backward. Space doesn't instantly freeze you either. Even though the vacuum itself has essentially no temperature to speak of, there's also nothing there to conduct heat away from your body quickly, since a true vacuum contains almost no matter to carry that heat off. Your body would actually lose heat quite slowly, primarily through radiation, the same way a thermos loses heat slowly compared to an open cup, meaning temperature is far from the most urgent threat you're facing in those first critical seconds. Meanwhile, any skin facing the sun directly could suffer severe sunburn from unfiltered radiation within minutes, while skin in shadow, just inches away, stays intensely cold, a strange split experience with no equivalent anywhere on Earth's surface. If rescue and repressurization happen within roughly 90 seconds, NASA's own research suggests survival is genuinely possible, along with a real chance of a full medical recovery. Beyond that window, oxygen deprivation to the brain becomes the dominant, and ultimately fatal, threat, the same way it would in any other setting starved of breathable air. That's the edge of what we know. The human body turns out to be remarkably well sealed against vacuum, resilient enough to survive brief exposure through nothing more than ordinary skin and blood vessels, without any of the explosive drama fiction has trained us to expect. So here's the honest answer. Exposure to the vacuum of space is genuinely survivable for a short window, thanks to how well ordinary human skin and circulation contain internal pressure without any special equipment at all. But the true danger isn't cold, and it isn't your body bursting apart in a dramatic explosion. It's the silent, remarkably fast loss of oxygen from your blood, racing against however many seconds it takes for help and repressurization to arrive. There's another place in our solar system where the danger is completely different, not sudden but permanent. What happens if humanity actually tried colonizing Mars tomorrow? That's a story for another episode in this series, so subscribe if you don't want to miss it. I'll see you at the edge.